For section 3.1, we're going to look at what we call exponential functions and look at what their graphs look like. So up until this point, we've looked at what we call algebraic functions. And these algebraic functions are polynomials and the rational functions that we looked at in the last section. In this particular chapter, we're going to look at what we call non-algebraic functions. And so these are exponential functions and logarithmic functions. These two categories of functions are what we call examples of transcendental functions. So what we're going to first look at in this particular section are exponential functions. When we have an exponential function, we say the exponential function with a base a is denoted by this here. F of x is equal to a to the x. A is greater than 0 and not equal to 1, and we want x to be any real number. Now, of course, if a is equal to 1, we wanted to exclude this a is equal to 1. Why? Because when we do not exclude it, we'll have 1 to the x, which of course is 1. And we know that 1 to the x is a constant function and not an exponential. So for these purposes, for exponentials, we're going to exclude 1. Now, we've seen exponential functions before, but didn't think about them as exponential functions. For instance, this here. This 4 to the third is equal to 64. We've done that several times, just in general. But in this case, our 4 is our a, and our 3 is our x. And we can look at it here. 4 is a again, but in this case, our x is 1/2. And of course, 4 to the 1/2 is equal to 2. But for those cases that we've seen, we've used just rational numbers. Now we want to look at irrational exponents for our functions. So when we think of an irrational number, the square root of 2 is an irrational number, and it doesn't repeat or terminate. But what are we doing? Since we can't get an exact value, what we're doing is we're doing an approximation of numbers getting closer and closer to this value. And so we see here if we start with 1.4 and we work our way until we get it. And of course this goes on to infinity because this is an irrational number. To evaluate these exponential functions, then we actually have to use our calculator. The ones we saw earlier are easy to calculate, but when we're looking at irrational numbers or numbers that aren't just integers, it's sometimes not as easy. So what we want to do is evaluate, say for instance, 2 to the negative 0.1, or 2 to the negative pi. And pi, of course, is an irrational number. And what I want you to do, and then our last one is 0.6 to the 3/2. What I want you to do now is to pause, pull out your calculators, and actually do these calculations. Plugging negative 3.1 for your exponent, 2 to the negative 3.1, you should have this value here. Raising 2 to the negative pi, you should get this second value here. And 0.6 to the 3/2, you should get this value here. If you're not getting these values, then you should see me or someone to make sure you're plugging it into your calculator correctly. So just as we have plugged into the calculator to find these values, we don't always need a calculator if numbers are prettier for us. So what we want to do is we're actually going to sketch these graphs here. And how we're going to sketch the graphs without knowing what it looks like, we're just going to plug in values. Let's look at the function f of x is equal to 2 to the x. So if we're plugging in numbers, for negative 3, we'll have 2 to the negative 3. And what do we know about 2 to the negative 3? When we have a negative exponent, we can make it positive by putting it in the denominator. And so we have 1 over 2 to the 3, which is 1/8. So when we get 2 to the negative 2, it's 1 over 2 to the second, which is 1/4. And likewise, we can continue plugging into the function, and we'll get these values here. Now we're going to also look at this g of x is equal to 4 to the x. Doing the same thing we just did for 2 to the x, we're going to get these values here. So for instance, 4 to the negative 3, we will have 1 over 4 to the third, which is 1 over 64. And we can go through this same pattern here to get this full line. So now what do we notice? If we plot these two here on the same graph, it will look as it looks here. This is our f of x is equal to 2 to the x by plotting these points. And this here is equal to our g of x is equal to the 4 to the x, plotting these points here. We notice that both of these graphs are always increasing. The values are always getting larger. Okay. But we notice that this 4 to the x is getting larger more rapidly, quicker than the 2 to the x is. Now let's look at the two functions h of x is equal to 2 to the negative x and j of x is equal to 4 to the negative x. So these are the values we get. How do we get them? For instance, if we're finding this value here, we have 2 to the negative of a negative 2, which of course would be 2 to the 2, which is 4. So when we get down to say this value here, we have 2 to the negative and now this 2, which of course we've seen, of course, is our 1/4, which we see. So plug in these values, and now we're going to plot these values for the graph. Plotting these values, we get these two functions, two graphs here. Okay, in red, we have our 2 to the negative x. In blue, we have our 4 to the negative x. What do we notice about these graphs based on our other graph? We notice it appears to be a reflection about the y-axis. So if we're looking at 2 to the x is our, say, parent function, f of x. If we look at this, I think it was h of x is 2 to the negative x, we know f of a negative x, which is equal to f of negative x, tells us we're going to have a reflection about the y-axis. And so our 2 to the x would look something like this. And then our negative x here would be a reflection of this. So what else do we notice? If I have 2 to the negative x, let's rewrite this, of course, as 1 over 2 to the x. We can also notice that this is the same thing as 1/2 raised to the x power. And so in a little bit, we're going to see the relationship between this function with a positive exponent and this function with a negative exponent. So let's look at the characteristics of this exponential function. We've seen the graph. I actually want to go back a couple of slides and see something. So on all the four graphs we've drawn, what is one thing we notice? Anytime I put in a 0, say so 2 to the 0 I get 1, 4, to the 0 I get 1. Even when I had 2 to the negative x, 2 to the negative 0 I get 1. So what do we notice about our graphs? We notice that it always goes through the point 0, 1. And this is going to be one of the main characteristics we're going to know about our exponential function. It will pass through the point, always through the point 0, 1. So, back to our characteristics of the exponential function. This is the general form of what our graph of a to the x looks like. It again, of course, passes through the point 0, 1. The domain of this function is from negative infinity to infinity. Why? Because I can put in any value of x and get a value for y. but the range is only from 0, from 0 to infinity, because these are the y values that I will actually have. And so the range is from 0 to 1. We see also that our y-intercept is 0, 1. The function is always increasing. And we notice that the x-axis happens to be a horizontal asymptote. We say this function is continuous because there are no breaks or holes in this function. Now let's look at the function of a to the negative x. And so we see here, we can look at it in a different form. We also, when I simplified it, notice it's also a to the x. So remember we had 2 to the negative x, and we wrote that as 1/2 to the positive x. So the graphs of a to the negative x, which is here, is the same as the graph of any number between 0 and 1 raised to the x power. Because when we simplify, they become the same function. The domain is still the same, from negative infinity to infinity. The range, again, is from 0 to infinity. It still goes through this point, 0, 1. This time the function is always decreasing. We have a horizontal asymptote at the x-axis. And this function is also continuous. And so we notice that the graphs of exponential functions will either always be increasing or always be decreasing based on the value of a to the negative x, or if our a is between 0 and 1. Okay, now let's talk about the shifts of these graphs. So let's look at, what is this? 3 to the x plus 1. Okay. So it wasn't supposed to pop up, but it shifts to the left by 1 unit. So if we look at this function, of course, when we write the parent function, this is our 3 to the x. So when we're drawing our shifts, we always look at that point that's stationary. That's the point 0, 1. So that's the point that we're going to shift. And since we have this 3 to the x plus 1, that tells me I'm going to shift to the left by 1 unit. So this becomes my new point, which will be at negative 1, 1. And so now my new graph will be this 3 to the x plus 1. Okay. Now let's look at 3 to the x minus 2. If we look at this graph, of course, our parent function is my 3 to the x. And again, that point of interest is my 0, 1. And so the minus 2 tells me you're going to go down 1, 2 units. And so now here will be my point of interest. And this is my new graph, 3 to the x minus 2. And so what happens? It is a shift down by 2 units. What about a k of x is equal to negative 3 to the x? What does a negative in front of the function actually tell us? It gives us a reflection about the x-axis when it's a negative of the function. So what would that look like? We have, of course, our regular function, 3 to the x. And so if we have 3 to the x, and this is a reflection, of course, our point here again is 0, 1. If we have a reflection about the x-axis, this is our x-axis here, then this point now becomes this 0, negative 1, and our new graph will look like this. So this is a negative 3 to the x. It's a reflection about the x-axis. Now I have 3 to the negative x. And so what does that tell us about the function? We have a reflection about the y-axis. And so we've actually seen this. This is our 3 to the x, And so reflection about the y-axis, we actually have seen, so the points stay the same. Oh, excuse me, this point of interest stays the same. This is our 3 to the negative x. So we saw these functions earlier when we were looking at a to the x and a to the negative x. And we said it's just a reflection about the y-axis. And so we do the same shifts and transitions that we've done before in the past. They still apply for exponential functions. So now, if we were to draw these functions, we know it's a function because it passes the horizontal line test. And anything that passes the horizontal line test means that it is what we call a one-to-one function. And so therefore, we're going to use this one-to-one property to actually solve some equations of exponential equations. And so what is the one-to-one property? So of course let me go back. So our one-to-one property says that, of course, a is greater than 0, a not equal to 1. If I have this a to the x is equal to a to the y, this is true if and only if x is equal to y, which would make sense. If I have 2 to the 3 is equal to 2 to the x, then that would mean that this x must equal 3 for these values to be the same. So let's look at a couple examples. So life always isn't so pretty for us. Okay? Sometimes our bases are not the same. So we have 3 to the x plus 1 is equal to 9, which is an exponential equation. So what do we want to do the one-to-one property? Our bases, we call the 3, our base here must be the same as this base here, 9. So we have 3 to the x plus 1. And how can I get this 9 to have a base of 3? We can rewrite 9 as 3 squared. So what do we notice? We now have the same bases, and so therefore our exponents must be equal to each other. So we can say that x plus 1 must equal 2. Solving this equation, of course, we get subtracting 1 from both sides, we get x is equal to 1. And let's see if that looks the same. If we were to plug back into our original function, 3 to the 1 plus 1, does this equal 9? 3 squared, does this equal 9? Of course, 3 squared equals 9. And so this is how we solve using the one-to-one property. Sorry, let me go back. Now, let's look at this 1/2 to the x power. Okay, how can I rewrite that so that it looks like our, so we have the same base? What can we do here? Of course, I can rewrite this as 1 to the x over 2 to the x is equal to this 8. And of course, 1 to the x is just 1. Sorry. And I can bring this 2 to the x to the numerator. If I bring it to the numerator, it becomes 2 to the negative x is equal to 8. And so now I can get this 2 to possibly look, this 8 to look like a 2, and we see 2 to the negative x is the same thing. 8 is 2 to the third power. So what does that tell us? This negative x must equal this 3. So we have negative x equal to 3, and so our x should be equal to negative 3. And you can plug it back into the original equation and see that it holds. Now, and sometimes we're going to talk about now this natural base e. And so sometimes we see this e often in everyday occurrences, and this e is a value equal to 2.7182 ... It is an irrational number. We're going to call this the natural base e. Okay, and so looking at the natural base e, we can draw the function by plugging it in. If our base is e, if we do this function, e to the x, of course, if I plug in e to the 0, I still get my 1, so this point is still on the graph. And then plugging in, we notice that the graph looks the same as we have looked for the same as our a to the x. But in this case, my base a is equal to this number e, which is 2.7182. Now keep in mind, e to the x looks like we have two variables. E is not a variable. E is a constant, which is equal to this value. There is a button on your calculator that will give you this value. And x here is our variable. And so, just like we can plug into our calculators to get these values, we can plug into our calculators to get the values of e to a function. So, I would like for you to go through and pause and plug into your calculators each of these values. So we'll start with e to the negative 2, and you should get this value on your screen. E to the negative 1 should give you this value. E to the 0.25 will give you this value. And e to the negative 0.3 should give you this value. Go through, and if you're having problems with getting these values on your calculator, again, see me or someone to help you to make sure you're plugging them in correctly.